Alright, so I finished the previous video with this set of rules for limits. And here we have the addition rule. The sum of two sequences go to the sum of limits. Subtraction rule, that's just about the same thing. Multiplication rule. And he gives a special case of the multiplication rule when one of them is a constant. Now, of course, the limit of a constant sequence is that constant because it doesn't change. Right? So you can multiply a sequence, and the result goes to the constant times the limit. And the division rule, which is like the multiplication rule. All right. So the way you prove this is with the definition, and you can convert all of these to statements about conversion to zero, right? This is the same thing as saying an plus bn minus l minus m converts to zero. And you prove this using these epsilons, all right? So I will not be doing any of these proofs right now. I may ask you to do some proofs later, but these are kind of technical. The important thing I want you to get right now is the intuition. That certainly, if an eventually gets within epsilon of L and bn gets within epsilon of m, and an plus bm is going to get within, well, it's going to get within 2 epsilon of L plus m. And don't worry about the 2, because if epsilon gets as small as you want, 2 epsilon also gets as small as you want. So we may do something with that later. All right, but let's get the intuition first. Now, we've been talking about limits of sequences. Now we want to talk about limit as x changes. Now, x is not a sequence. X is continuous. It's not discrete. It's not something that you can enumerate like this. But x takes values that vary, well, they vary continuously. Right? So, for instance, as x approaches 0, what about the function 4 minus x squared? Well, the x squared term becomes negligible and you get 4, right? As x approaches 2, the function 5x approaches 10. Okay, now look at this statement here. If x is close to a, then f of x is close to L. All right, now this is quite similar to what we have up here with the limit of sequences. Here we're saying that if n is greater than n, then an is less than epsilon. In other words, if little n is large, then an is close to 0. All right. Now, if you translate this to the limit as L, this would say if little n is large, then an is close to L. So here you're saying as n gets large, the values get close. Here you're saying as x gets close, the values get close. All right. So he has this picture down here that illustrates this. Here you have a graph, and here you have a function. And here you have a small interval of x. All right. Now you can see that if you have a small interval of x, then there's a small interval of y that the function lies inside. And that's because there's no jumps in this function. See, this function has a jump, and that's not true. This function has a step, and that's not true. So what's distinguishing this function from these others is that this function is continuous. And here this says that if the x is in a very small range, the y will also be in a very small range. And furthermore, if I specify my y range, I can choose a small enough x range to make the function lie in that y range. Same thing we had up here with the limits with n. Here we said if I choose any epsilon, then I can find a n, which may be very large. I can find a n such that the values of the sequence stay within epsilon of that n. Remember the limbo idea, that after some time, I'm always able to go under the limbo bar. So that's the same thing here. After some time, or for a small enough window, not after some time, but for a small enough window, I can guarantee that my function is inside this vertical window, right? All right. So think about it that way. Given a vertical window, there's always a horizontal window that's small, makes sure that the function stays in the vertical window. All right. In fact, in this case, I could have chosen a larger horizontal window, right? Because over here, the function is still inside the vertical window. So in fact, I could have chosen the box to be this big. You should have drawn this so that it goes outside like that. But the point is not to find the delta that's the biggest delta that works. The point is that there is a delta. There is a horizontal window that guarantees that I'm within this vertical window. Okay, here's the process of proving limits. We'll go through this and prove that the limit as x goes to 2 of 5x equals 10. So in this case, I'm looking for the a equals 2 and L equals 10. So in fact, this value here, a is 2 and L equals 10. Now certainly you can recognize this as a straight line. All right, let's go ahead and draw a picture, see what this looks like. All right, now when I draw this picture, I'm just going to draw part of the axes because of the range we have here. Here's going to be the point, I'll call it, this will be the point 210. Now we know that this 5x, that's a line with slope 5. So here I'll write this is y equals 5x like this. And if I go down to the x-axis here, this would be the point x equals 2. Okay, and if I go over to the y-axis here, this would be the point y equals 10. Okay, I'm not going to draw the full axis. Well, I guess I can do that, but the y scale would be different from the x scale. All right. Now the point is I can choose an epsilon, 10 plus epsilon, and 10 minus epsilon. Here's my window. And then let's go ahead and draw some bars here. So that's my vertical window. Now you can see that this crosses at 2 points. In fact, you know what these 2 points are. Okay, this is the point, since this has y coordinate 10 minus epsilon. You can figure out what the x coordinate is going to be. Well, 2 times, it's going to be this divided by 2, so that's 5 minus epsilon over 2. And here's the point 5 plus epsilon over 2, and 10 plus epsilon. Okay. All right, so the statement you have here is if x is within epsilon over 2 of 5, so I can say if x is between 5 minus epsilon over 2 and 5 plus epsilon over 2. Sorry, did I say epsilon over 2? Got that wrong there. It should be epsilon over 5, right? Not epsilon over 2. Good thing I caught that. All right, let's fix that up. That's not a 2, that's a 5. Right? Because if I multiply, I have to multiply this by 2 and get this, so it should be 5 plus epsilon over 5. Let me double check this, make sure yeah, that should be epsilon over 5. It's not, and it's not 5 plus epsilon over 5, it's 2 plus epsilon over 5. So I kind of got that whole thing backwards. Let's fix it up and we'll get it right. Right, yeah, it doesn't kind of make sense if you have 2 there, so we'll do that. All right. If you were on the ball, you caught that. All right, so let's go ahead and do this. All right, so here we have, this one is going to be 2 minus epsilon over 5, 2 plus epsilon over 5, right? And then this is 2 minus epsilon over 5. Okay, so that means if x is between 2 minus epsilon over 5 and 2 plus epsilon over 5, then 5x is between 10 plus epsilon and 10 minus epsilon. All right. The other way, of course, you can write this is that if x minus 2 is less than epsilon over 5, then 5x minus 10 is less than epsilon, okay? Okay. So you can say if I'm given any epsilon greater than 0, I can choose delta is equal to epsilon over 2, and the condition holds. Okay, and what that means is that the limit as x approaches 2 of 5x equals 10. Okay, so given any epsilon, I can choose an appropriate delta. Now I could have chosen delta equals epsilon over 3 as well. That's smaller than necessary, but that's fine. All right, notice here you have less than signs in both places. That's a technical point, but it's kind of important. So actually in mathematics, what you often, this is epsilon over 5. I don't know why I keep wanting to say epsilon over 2. Sorry, it's epsilon over 5. Okay, all right, so back to my point. Mathematicians often choose their delta to be a little bit smaller just to give some leeway. You don't have to be so careful about finding the exact delta that works. All right, just so long as you get one that is small enough. All right, so hopefully you can see why this definition fails here. If I get closer and closer to, all right, so here, in fact, if I get closer and closer to A, the value of f gets closer and closer to L, even though f of A is not equal to L. So in this case, f of A is not equal to the limit of f as x approaches A. All right, so in this case, the function is not continuous. If the function is continuous, then the limit has to agree with the function value. Okay. In this case, there's actually no limit at all, because as your x gets closer and closer to A, you get ambiguous signals. If it gets closer to A from this side, it gets close to this value. If it gets close from this side, it gets close to this value. There's no single value. In this case, the limit does exist, but the limit is not equal to the value of the function. All right, and you can see that visually. Very nice that that's reflected in the graph. You can see that. If there's a jump, then it's not continuous. All right, let's go through these points, make sure we've covered them. First of all, you choose the height. Socrates chooses the height, and Plato gets to choose the width. So that's the game. You choose the height, then someone else chooses the width, and the width has to be narrow enough. Okay. Second one, if the function has a jump, then there's no way you can get a box that holds it, right? Okay. I can always choose this height to be smaller than the jump, so that function is not continuous. Second remark, as I mentioned, when you're taking limits, you don't ever refer to the value of the function at the point. You're only finding the value of the function close to the point. All right. So in fact, the limit here is well defined, even though the value of the function is not well defined. Right. And he refers here also to the definition of continuous function. If the limit of the function agrees with the function is continuous. Okay. All right. So here we have a case where this number 5 was the slope. He says, this choice barely kept the graph in the box, as I mentioned. Make it a little bit narrower, and the graph goes safely out the sides. A reasonable choice is to divide epsilon by 2 times the derivative. Okay, we double the slope. Notice here we divided by the slope. Here he says divide by 2 the slope, 2 times the slope. That's going to be safe. Okay. Right. So, like I said, you sometimes make this a little bit smaller than necessary. Well, here's an interesting example to look at. So let's take a look at this one. Again, it's good to picture what's going on and not just look at it algebraically. So we'll go ahead and copy this and see what it looks like. All right. You can graph this function. It's a square root function. Now you know that a square function is a parabola going up. A square root function is a parabola on its side. All right. So let's see. Here we have square root of x minus 1. Now we know when x equals 1, y equals 0. So we're looking close to x equals 1. So here we have the x equals 1. Let's go ahead and make this red. And it turns out that this function looks like this. It's a parabola on its side. All right. Now here you can visually see that this function is continuous. But the problem is that as you get closer and closer to the point here, the slope is getting larger and larger. All right. In fact, if I take this point here, if I go up to epsilon here, right? All right. We can actually solve for this. If we have square root of x minus 1 is equal to epsilon, then that tells me that epsilon, then let's say x is equal to 1 plus epsilon squared. Okay. All right. So this distance is only epsilon squared. Now if epsilon is small, epsilon squared is much smaller than epsilon over 2. All right. So we can actually choose, in this case we could choose delta equals epsilon squared over 2. And that means my x is closer than this point. Right? So you don't always want to take the slope divided by 2. If there's no slope, then you may have to do something else. All right, so let's see if he makes that point. So you're just going to say that, he's probably going to say the same thing here. Okay, now last thing we have here is the squeeze theorem. And rather than going through the proof, let me draw the picture. All right, it's always good to know what you're proving. That's one drawback with this text, is there's really not enough pictures. Hopefully I can remedy that in my lectures. I will try to draw more and more pictures for you. Okay, so let's go ahead and take this. So what is actually going on here? Okay. All right, so the hypothesis is that g of x is between f and h, and also that f and h go to L. So let's go ahead and draw this picture. I've got my multicolor pen, so we can do this. I'll make F blue, we'll make blue, red, and green, which is fine. It's okay. So here's my axes here. Okay, and then here I'll make F. I have to be a little bit careful here. So here's my, oh, I guess I'll make my F red. Okay, so here we'll do F is something like this. Okay, this is f of x equals y. Okay, and then let's make my, and h is on the top, so I'll make h blue. And I'll target this point here. So here's my h. And then we'll paint that point there. Okay. Now G is between these two, so we'll get out the green. And G is in here. Okay. Okay. And then what do we have here? This is the point A, and this is the point L. Okay. You can see that the limit of f of x is L, right? It gets closer to this value. The limit of g of h of x is L, and g is caught in between. So there's nowhere for g to go except pass through L. So it's like a, certainly like a bottleneck, or the squeeze theorem, right? So g has to thread the needle here. Okay. Now here he also makes this caveat. This only needs to be true for x near A. I could have chosen my h to go down out here. We're only looking at values near A. So it's not really necessary that f is always less than h, as long as there's some neighborhood where f is smaller than h. And the limit of f at A is equal to the limit of h at A. All right, so that's your squeeze theorem. And that's it for this section.